Hi. So welcome back, everyone. For those of us who are joining me for the first time, hi. This is a course on quantum mechanics, um, specially aimed at undergraduate students and advanced high school students. And the book we are following together is called Introduction to Quantum Mechanics by David Griffiths. It's a universal book that's taught both in the IITs, IITs, as well as in the more global universities at an undergraduate level. This is my YouTube channel where I upload these videos regularly. You can go check it out. It also has, I'm a researcher in Seoul, South Korea. So this channel also has various tidbits and trivia about my life in Korea, about scholarships, about physics research, etc., etc. So I request you to all check it out and like and subscribe. Thank you. So without further ado, let's begin. These were the notes from last time, and let's start. So yeah, this is lecture 2. Also goes without saying that if you have any questions from last time, feel free to mail me. The mail address was given in the first page, and I occasionally check the mails and I respond to them, and hopefully that would be helpful. Right, so where were we last time? We wrote the Schrodinger equation, right? We wrote the Schrodinger equation here, and that's where we'll start from. So where was the Schrodinger equation? This was the Schrodinger equation, right? Let's start from here. This was the starting point, and I had mentioned that these wave functions psi x of t, when integrated over gives you probability densities. Rather, probabilities actually. These are probability densities themselves. That is, the probability of a particle lying between, say, x a and x b is going to be given by and explain that you need a mod because these are typically C functions, right? Of course, this is naturally less than equal to 1 because it's a probability. So there will be a suitable normalization. For the wave functions. Right. So, next question that I want to do is an interlude into probabilities. Maybe some of you already know some of it, but nevertheless, it doesn't harm to describe it once again. Okay. So maybe I'll just maybe this is better explained with just an example. Okay. So okay, formally first, and then I'll explain with one example which would help clarify. Say you have a set xi, which basically means, say, x1, x2, it's a set to xn. Then right now, thing I care about the most is called the mean, which by definition also often written as simply x bar is given by 1 by n summation xi I running from 1 to n for this set. Very abstract, right? We'll just see an example in a moment. This is notation, this is no multiplication, xi or x bar, but I'll probably more often use this notation. Generally, these are in moments in probability, and the definition is expectation value of xn, which, extending this definition here, would simply mean that is, your x bar is simply the first moment. I would need a second thing, or a second measure as they're called, which is called, so this was the first one, second one, I'll write in the next page. Second one is called variance, which by definition is expectation value of this object. This is definition. Sorry. There's a square here. So this is simply expectation value, the second of the square minus square of the mean. This is also called mean of the square y minus, wait, let me finish this, minus square of the mean. This is the mean of the square, right? And this is the square of the mean, right? Do you see it? Because this bracket is the mean, and you have the 2 here, So this is the square. So this guy is the mean of the square. And likewise, this guy is the square of the mean. This measure is called the variance. And the last thing that we need is the square root of the variance is called the standard deviation. So lots of seemingly difficult mathematics going on, but these are very simple, and I'll shortly give an example which will help clarify matters. You could ask, is the square root well defined? And in fact, it can be shown that the variance is actually equal to 0, always. So there's no problem with taking the square root. It's a well-defined object. Good. Okay. Enough jargon. Example. This is most clarifying. So, what example do I want to give? Okay. Say you roll a dice. What is the mean of the number you expect? What do I mean? So you have a dice. Say you roll the dice. What is the mean of the number you expect to get? Okay. So we already have the formula. So first, before that. So if I roll the dice, what are the possible numbers I can get? The possible numbers I can get are 1, 2, 3, 4, 5, 6, right? These are the standard numbers that you get for rolling a dice. And assuming it's a fair dice, that is, each outcome, these are called an outcome, is equally likely. What does it mean? So probability of getting, say, a 1 is the same as probability of getting 2 is the same as probability of getting 3, up to probability of getting 6. And if you do roll a dice, you will get something, either 1 or 2 or 3 or 4 or 5 or 6. So, of course, we know this is what I mean, by the way, by saying they are equally likely. It's not a loaded dice. So P1 plus P2 plus ... up to P6 should be 1, right? You should get something. Which means, just to introduce a notation, which means pi is 1 by 6. This is equally likely. All of them are equally probable to happen. So I runs from 1, 2, up to 6. Good. So now we are all set to compute the mean. So what is x bar? Which as a notation is also the same as this. We had written this formula, right? Xi, where we have discussed Xi is basically this set of numbers from 1 to 6. Of course, n is 6. So this is immediate. This is 1/6. 1, 2, plus 6. And you can calculate and show that this is actually 3.5. Yeah. This is the mean value. Not hard, right? It's very simple. Okay, so what about the second moment? The mean was the first moment, right? So what was the definition of second moment? Second moment was simply this. Recall, nth moment was the expectation value of x to the power n, right? So the second moment is this. And now you all know how to write this. So it should be 1 by n summation xi square, which in our context means 1 square plus 2 square plus dot 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 6 square, which you can calculate and show that this is actually 15.17, right? Good. So I've calculated mean. Calculated the second moment. And let's calculate the variance and then the standard deviation in this simple example. Variance. So definition of variance was, they are equivalent. X minus x bar whole square. This is the definition of variance, sigma square, which is the same thing. It's just one line computation to show that this is actually, yeah, say it with me. So this is what? This is the expectation value of the square, or the mean of the square, same thing, minus the square of the mean, right? We derived this formula here. It's this formula that I'm talking about. This is great because I know both the objects. I've already calculated both the objects. So this is 15.17 minus 3.5 square. And this turns out to be 2.92 something. And as claimed, this is positive. Which implies sigma is 2.92, which is 1.7088. So let's do a case 2, and maybe that will help us understand what's actually happening. Imagine now you have a crazy die where instead of the faces showing different values, say all of them show the same value, 3. Crazy die. Crazy dice, correct. That is, the set now is basically 3, 3, 3, 3, 3, 3. All of them, all 6 of them. Right? So think fast. What's going to be the mean and the variance? At least what's going to be the mean? Exactly, 3, right? So let's see. What is the value of the mean? Again, x. Same formula. It's just that each xi is now the same. The value of xi, all xi's are actually 3 for all I. This is a notation that people use in science. This notation means for all. So you should read this as xi equal to 3 for all I. Okay. Okay. So this is 1 by 6 times 6 into 3, because all the xi's are 3 and there are 6 of them. So xi is actually 3, right? Not surprising, because you had only one value, right? So the mean is also the same as the value itself. Let's compute. The variance and the standard deviation. And there's a reason why I'm doing this exercise. It will teach you something about what the standard deviation is. Okay, so while I'm writing, you also write on your pen and paper what the formula for variance is. So sigma square variance is basically the second moment. So this is 1 by n summation xi square. That's the difference, right? The variance, the difference with the mean and the variance is this square. So variance has a square. Okay, maybe what I should, okay, let me take a step back actually. Let's first, like we did in the last example, first let's figure out x square. You know, I'm being extremely pedantic, but it's okay. Xi square I equal to 1 to 6. Again, recall all your xi's are 3 for all I. This I have already calculated to be 3, and I have defined variance as Okay, good. So this I know already. I need to compute this guy now using this formula, right? Very easy. So 1 by n is 6. So summation 3 square, maybe without, don't need the summation, 3 square plus 3 square plus 6 times, because n is 6. So this is simply 3 square, right? And lo and behold, your variance is 3 square minus 3 square. This is x square and this is x square. Okay, although they have the same value, they are actually two different things, right? They have the same value because you have a very crazy die here. It won't generally, of course, have the same value. In fact, we have seen that they are not of the same value here and here. And in fact, it also holds that the variance is a positive definite quantity. So lo and behold, you saturate the bound, or in other words, you get a zero. This is also a physics terminology or terminology used in science. When you have something like this, a greater than equal to or less than equal to, and when you pick out the extremal value, which in this case is 0, it's expressed as by saying that you saturate the bound. Okay, so now that you have 0 here, it means that you have saturated the bound, which of course also means that the standard deviation is 0 because it's square root of sigma square. Good. So what does it tell you about standard deviation? Why did I do all of this? Well, it actually tells you. So what does mean tell me? It's also called the arithmetic mean, actually. Aside, there exists geometric mean. You have all learned in school, as well as harmonic mean. But the mean here is the arithmetic mean. It tells you the average value, right? This tells you the average value. It does not tell you how the values are spread. How the values are spread are captured. There are actually very many more measures, but one of the measure is the standard deviation. Tells you how the values are spread or in other words, Imagine these two graphs. For example, okay, maybe the previous one was better. But anyway, imagine this graph. So this is marks obtained in an exam, say by some students. This is the number of students. And typically the kind of graph that you get is something like this. Right? Like this is the average. So this, firstly, this is the average. It lies in the somewhere in the middle, right? Somewhere here. So there's, I mean, on either side of the average, the number reduces. So say 50 people got this marks, but 30 people got this marks, and 10 people got this marks, and so forth, right? And it happens also in this way, say 10, etc. You could have a, so the average here, let's call it, say 50. It's this value. Not 50. So the average marks is, say 70. So it's a good class. This is the average mark, say 70. And this is the number, okay? Number of people, say, who got this mark. This is another graph, say of the same exam, but in a different class. A different set of people, say, took the exam. Again, imagine this is the marks. This is the average marks. Here also say it's 70. Say, so this point is 70. So you see, X bar, or the mean, does not distinguish between this case and this case, case 1 and case 2. Okay, the mean is the same, the average marks is the same. Okay, but clearly this class is different from this class. For example, here there seem to be some students who are struggling and who need to study harder. Some people are geniuses, etc., etc. But this seems to be a much more, but this one seems to be a much more homogeneous class, right? So there are very, very few people who are struggling, and yeah, most of them got this average marks. So it's a more homogeneous class, and everybody is sort of getting the same marks. It also seems to suggest that everybody cheated from the same paper. But jokes aside, what I want to emphasize is this mean itself does not distinguish between this and this. The mean is 70 in both the cases. But standard deviation does. Okay? Standard deviation actually tells you this width, for example. This width and this width. So clearly you see this has higher standard deviation. This has lower standard deviation. Captured by the width here being higher versus, say, here being much less. So this is where this is why we want to distinguish between this case and this case. So one of the measure is actually the standard deviation, and you see this to be panning out here, right? When you had all the numbers to be the same, you see the standard deviation is much less. It's actually 0 because numbers are all the same. So this corresponds to this case, right? All the numbers are, for example, 3 here. So it has just it's like a spike. So 0 standard deviation. But the case before was more along these lines, right? The standard deviation is not 0. The numbers were distributed from. Actually, this was not a continuous graph, but that's okay. The number was 1, 2, 3, 4, 5, 6, something like that, right? So yeah. So this highlights these two cases. Highlights the difference. The role plays. Explains the role of standard deviation. Good. So what does all of this have to do with quantum mechanics? Well, because I mentioned that quantum mechanics just tells you probabilities, right? So the above setup will be generalized good. So let me briefly show you how the generalization happens. So for example, we had one by n, for example, xi. In our dice case, recall this was something like this, because and what was your 1/6? What was this 1/6? Well, this 1/6, if you go back a couple of pages, you see the 1/6 was actually right here. It's the probability, right? And it was 1/6 because it was all events were equally probable. So this 1/6 is actually, in hindsight, this is the probability, right? Is this clear? This is important. This 1/6 was actually the n inverse. 1/n was actually probability. So 1/n for equally likely events is basically the probability, right? So this you can write as, in fact, this is the more general definition. So probability, this means probability of event xi happening and this is the value, of course, which you have seen so far, sum over all, say, n in the general case, 6 in the case of dice. This formula would be generalized in a very obvious way in quantum mechanics. This formula, let me write it again, pxi xi. So this was for the discrete system. Labeled by i's, right? It's a countable number. It's a discrete label, 1, 2, 3, 4. I goes from 1, 2, 3, 4, etc. So that's why it's a discrete system. To the continuous one. And we already know how to do it in going to the integration domain. We have learned this in school, right? Sum goes to integration. So we'll do exactly just that. x variable psi x t. This is the, so in quantum mechanics, expectations value, this is expectation value of x, say. It's an operator, but that's not important right now. So what did we do? Should I, maybe I, even to make things even more apparent, maybe I should write it in this manner. So you see, three things happen, right? The sum went to the integration using something that we already know from school. I have mentioned that this is actually given by, this actually gives the probability, the wave function. That was the whole point of quantum mechanics, that the probabilities are given by the wave functions. And this x goes to x, simple. Of course, it cannot have a discrete label because now it's a continuous variable, right? So the label, of course, is gone. And the label, the sum over I goes to, say, integration here. So yeah, this is the formula that I wanted to derive. And this is a standard formula, not just in quantum mechanics. You would pretty much use it even for, if you people take up physics later, you will use it even in quantum field theory, and so on and so forth. And analogously, equations, recall, pi was 1. We have seen this, right? It just tells you one of, like when you roll a dice, it just tells you that one of the outcome has to come. Like it has to be either 1 or 2 or 3 or 4 or 5. And we have seen this because we have seen pi to be, for example, in the previous case we discussed, for I equal to 1, 2, up to 6. So this certainly holds, right? Because this summation is pi to 6 is equal to 1/6 plus 1/6 plus 1/6. 6 times is equal to 1. The analogous equation in quantum mechanics is exactly the same. dt, what psi x, sorry, I'm using capital psi, right? Yeah, I'm using capital psi. One. Why am I using t here? Sorry. Yeah, this variable should definitely be x. My mistake. This, the left hand side actually gives you a function of t. Yeah. So this is the analogous equation in quantum mechanics. That the integral over the amplitude, square of the amplitude over all space, gives you 1, exactly as this equation. That's it, I think, for today. So yeah, so maybe we should have a tutorial session soon. where we use all these ideas to calculate. And yeah, as I mentioned last time, that please subscribe to my channel. The reason is that it will tell you when I'm uploading these videos, and we can form a community where we solve problems together, where we discuss things together. So yeah, my YouTube channel is Ray dash Physics Made Less Scary, and please like and subscribe. So yeah, see you next time. Bye bye. See you next time.